the hillside, they were called in from the glade.
The world is far more fragile than we take it to be. One spark, one fuse, and the powder keg goes off. Everything changed when the bombs fell. A change precipitated by the chain decomposition of uranium-235 known as fission, releasing massive amounts of energy into the environment. Though sometimes you can use plutonium-239 for a similar effect. Also, a lot of modern bombs use fission to start a fusion reaction with hydrogen to get an even bigger explosion. I'm getting off topic. Where was I? Right. Whatever started the war has been lost to time, as well as the kind of lives people used to live. The world is cruel now as we deal with the fallout. But if my studies of high-level nuclear physics have taught me anything, it's that radiation never changes. Everything is connected. To learn anything, you have to build on what you already know. Whether it's science, art, or philosophy, we can connect everything to anything. So let's learn anything. Let's find those connections and let's build our intuition. Noce, and you're being exposed to radiation right now. Don't be alarmed though, because radiation is a lot broader of a term than just the stuff nuclear power plants put out. In fact, anything that has a temperature, which is everything, is emitting radiation. So your phone, your TV, your pencil, even you are emitting radiation. So why is this the case? What is radiation? First, I want you to think about a fireplace. When you light a fire in a fireplace, the fire is certainly much smaller than the whole room. Yet, if you let a fire burn, the entire room will begin to heat up. Additionally, when you sit by a fire, you can feel the heat from it even though you aren't in the fire. So how does a fire affect things that aren't directly next to it? Heat transfer.
Overseas there came a pleading, help a nation in distress, and we gave our glorious laddies honor bade us do no less.
Heat transfer is an entire field of engineering and physics dedicated to studying how heat moves from one source to another. As a general statement, things at a higher temperature transfer heat to objects of lower temperature, similar to how water flows from high places to low places. In fact, historically, thermodynamic theories of the 18th century thought heat was a weightless fluid that moved from hot bodies to cold ones. Today, we know that temperature is better represented as the average kinetic energy of the molecules of a substance. That's a lot of words, but to break it down, I want you to think of billiard balls on a pool table. When given kinetic energy, the balls bounce around the table, colliding into one another and the side of the table. Sometimes one ball will be moving faster than the others, while the other balls will slow down until hit by another. If we average out the speed of the balls on the table, we will get a temperature of the pool table, so to speak. This is known as kinetic theory. That's an awfully hot bouncing dot. Now, we know that heat transfer results in the moving of energy from high to low temperature objects, but how does it accomplish this? Typically, we break up heat transfer into 3 different modes: conduction, convection, and radiation. But for simplicity, I will just go over conduction and then radiation. Conduction is the transfer of heat through direct contact. Like how metal bleachers or a car steering wheel is hot to the touch when it's been sitting in the sun. For gases and fluids, this is a little easier to picture. Think back to the billiard table example. Imagine we have 2 separate billiard tables being combined, one with balls moving faster than the other. As the 2 tables are combined, the faster moving balls will begin colliding with the slower moving ones, and eventually the new system will settle at a new temperature, a new average kinetic energy. For solids, it's a bit harder to picture. Imagine the balls are connected by springs. They will still move back and forth, but each ball cannot move freely, causing waves of energy to propagate between the solids called phonons.
For no guarantee no freedom to a tyrant's yoke should bend, and a noble heart must answer to the sacred call of a friend.
So now we move on to radiation. If we go from the atomic to the subatomic, we can remember from our chemistry episode that atoms have negatively charged electrons orbiting around them. From our power episode, we learned that when charged particles accelerate, they create a magnetic field, and vice versa. And from this episode, we have learned that atoms vibrate or bounce around constantly. Here's the question. What do you think would happen if the electrons started bouncing around? They move into different energy levels. If you recall from chemistry, these higher energy electron levels are less stable. So the electron will move back down, releasing energy. Since energy can't be created or destroyed, where does it go? Well, in this scenario, we have a charged particle accelerating and decelerating. So the answer is a magnetic field. And since we have a magnetic field being generated, we also generate an electrical field. And that electrical field then generates a magnetic field, and so on and on and on and on. All right, to summarize, electrons move up and down energy levels. The resulting drop causes energy to dissipate as a cascading wave of magnetic and electric fields. This is electromagnetic radiation.
Keep the home fires burning while your hearts are yearning, though your lads are far away, they dream of home.
All forms of electromagnetic radiation, or EM radiation, are restricted to the speed limit of the universe, the speed of light, which is about 300 million meters a second in a vacuum. What? Do you have to do that now? I'm trying to record. Do you want your room cleaned? Why don't you do it yourself? Why don't you buy your own place where you can clean wherever you want? You know, when I was a kid, I had to clean my home. Okay, ignore that. Not a cleaning vacuum, the empty void of space vacuum. So, all forms of EM radiation move at the speed of light, but we do have two knobs to turn to form different types of waves: wavelength and frequency. Wavelength is the length of the wave. It describes how long a single oscillation is, which is why we measure it in meters. Frequency is the rate at which oscillations occur. The higher the frequency, the more oscillations per second. We measure frequency in hertz. All right, Johnny, here's a rapid fire question round. What do you tell the doctor when you bang your knee? It hurts. What do you say when someone throws a Stephen King novel at your head? It hurts. What is the unit of measure for the frequency of electromagnetic radiation? It hurts. Perfect score, Johnny. Well done. Frequency and wavelength are opposite sides of the same coin. Higher frequencies have lower wavelengths and vice versa. The range of frequencies that EM radiation can take is known as the EM spectrum. At one end, you have long wavelength waves and short frequency waves like radio, and on the other end, you have high frequency and low wavelength waves like X-rays and gamma rays. In the middle, in a teeny tiny portion of the spectrum, from about 400 nanometers to 750 nanometers in wavelength, is visible light. Yes, anything that has color is emitting a specific frequency of radiation, just like a radio tower. Now, what does this have to do with heat transfer? To answer that, let's look at what a microwave does. A microwave generates waves with wavelengths in the micrometers. Since EM waves are oscillating electrical fields and water is polar like a magnet, the waves cause the water molecules to spin and move just like an electric motor, which we talked about in our power episode. And we know that an increase in average kinetic energy of particles yields a higher temperature. Earlier, I mentioned that everything that has a temperature emits radiation. So what kind of radiation do things emit? The wavelength that an object emits due to thermal agitation depends on the temperature the object is at. Short wavelength waves have higher energy levels than long wavelength waves. So the hotter an object is, the more of the emitted energy is projected into shorter wavelengths. This is part of the reason blue flames are hotter than red ones. Blue light is a shorter wavelength than red light. Interestingly, the Ray-Jeans law, which describes what specific range of wavelengths objects of a particular temperature emit, had a problem called the ultraviolet catastrophe that basically stated that all objects could emit infinite energy. This was eventually corrected with the help of quantum physics. But I digress. Alright, it's time to take a break. When we get back, I will go over what we typically associate with radiation: nuclear physics.
There's a silver lining through the dark cloud shining. Turn the dark cloud inside out till the boys come home.
Hello investors, here at Shutter Science we're not banging rocks together. We know how to make a thermonuclear power donut. With our patent-pending super heavy water, we pack 2 extra neutrons into our hydrogens. That's 20% more water per water. I wanted to sell it as a weight loss drug, but the lab coats tell me this stuff is more unstable than I am. But slam it into a magnet microwave and set it to high and you get the world's best tanning bed. I'm talking a self-sustaining Q1.2 fusion reaction that just keeps on giving. Just try to turn it off. I dare you. Thermonuclear apocalypse could happen and the thing will keep on churning. Throw it in your car, your house, or your national power grid for a future of clean, efficient energy. We also sell thermonuclear weaponry for the discerning customer. We are between banks at the moment, so make those checks out in cash. We're done here. Welcome back. Before the break, we discussed radiation as a form of heat transfer and as the light we are capable of seeing. Now, I want to branch into the field of nuclear physics and nuclear chemistry. At a certain threshold of energy, radiation has the ability to ionize atoms, or strip atoms of their electrons. This can be either through short wavelength EM radiation or subatomic particle radiation, which we can break down into alpha, beta, and gamma radiation. Alpha rays are essentially helium. It has 2 protons and 2 neutrons with no electrons. It's fairly unremarkable, as even a sheet of paper can block it. Beta rays are streams of electrons or positrons, which is the opposite of an electron, don't worry about it, that can have negative or positive charge respectively. While beta rays can penetrate more matter than alpha rays, it can still be stopped by a thin layer of metal. Unfortunately, there are no sigma rays, but we do have gamma rays. Gamma rays are the most dangerous of the group and require a thick amount of lead or concrete to stop them. They are very short wavelength EM radiation. This is the kind of energy we are going to focus on from here on out. So, what makes an atom release this kind of lethal energy? From earlier in the episode, as well as the chemistry episode, we learned that electrons in stable atoms can move into unstable configurations. Certain elements or configurations of elements are naturally unstable, and this is what we call radioactive. As a general trend, elements with an atomic number higher than 83 are radioactive to some degree, though there are almost an infinite amount of radioactive isotopes of more common elements. Isotopes are groups of atoms that have the same number of protons but a different number of neutrons. Since neutrons don't have a charge, all they do is add to the weight of the atom. These isotopes are mostly called out based on the number of neutrons in the nucleus. For example, carbon-14 is a carbon atom with 14 neutrons. In each case, the unstable configuration causes the atom to eventually decay, releasing alpha, beta, and/or gamma radiation. In some cases, an atom would have to decay multiple times in order to reach what's considered a stable configuration. Now, not all radioactive decay is made equal. The time it takes for an atom to decay varies from element to element and isotope to isotope. One way we can distinguish the rate a substance decays is through something called half-life.
Rise and shine, Mr. Freeman.
Half-life is a bit tricky to grasp because it is impossible to predict the exact time any given atom will decay. It relies on electrons, which have probabilistic nature dictated by quantum physics, which is, of course, beyond the scope of this lesson. So, to sidestep this issue, we are instead going to look at a larger set, a grouping of atoms. Imagine you gave 100 people each a quarter and asked them to keep flipping it every 5 seconds. If a person flips 3 heads in a row, they have decayed and leave the group. The outcome of each flip is determined by probability, and there would be no way to predict when any one person is going to flip 3 heads in a row. But using the fact that there's a 50% chance to flip heads, we can predict on average how long it will take for half the group to flip heads 3 times and leave. This is what half-life is, how long it takes for half a group of radioactive atoms to decay. With the quarter example, you can also think about how each time a person leaves, there are less people flipping quarters, and thus it probabilistically gets longer for someone to leave the group the more people leave. Let's say the half-life of this quarter experiment is an hour. That would mean it would take 1 hour to cut from 100 people to 50. Then, the principle of exponential decay would say that it would take another hour to cut from 50 to 25, an hour to go from 25 to 13, and on and on. So, the shorter the half-life, the faster the decay, and the faster the material emits radiation. For a few examples, carbon-14 has a half-life of about 5,730 years. Carbon dating actually takes advantage of this by comparing the amount of carbon-14 present in a substance to determine how long ago a living thing died. The more carbon-14 that has decayed, the older the subject. Potassium-40, the largest natural source of radioactive material in most humans and animals, has a half-life of 1.2 billion years. So fret not when you eat a banana. Finally, uranium-235, used in nuclear weaponry and energy, has a half-life of 700 million years. Surprised? Did you expect uranium to decay much faster? Turns out uranium is a bit more stable than you may have expected. But before you start licking uranium paint, let's put a couple things in perspective. Yes, uranium has a large half-life than a lot of other materials, but there also is the amount of a radioactive element that can result in a large dose of radiation. In the world, only 1 out of every trillion carbon atoms is carbon-14. About 1 out of every 10,000 potassium atoms is potassium-40. Bomb-grade uranium is about 90% uranium-235. And in the Earth's crust, uranium in all forms is 40 times more abundant than silver. So although uranium has a high half-life, it is by no means safe. Another reason why uranium is dangerous, and the reason why we use it in bombs and reactors, is that it is fissile, or capable of undergoing nuclear fission. A very small set of radioactive materials are fissile, and uranium-235 is the only naturally occurring one on Earth. In nuclear fission, very large atoms capture the energy of neutrons, a type of radiation we haven't talked about up until now. When fissile material captures this neutron, the new energy required to keep the atom together is higher than if the atom were to decay. The fissile atom breaks down into 2 smaller atoms and releases more neutrons, which in turn triggers additional fissile material to decay. The result is a chain reaction where each link generates more and more energy, resulting in either a high energy explosion or a consistent form of heat, depending on the percent of fissile material. We've taken quite a deep dive into radiation, from temperature to light and atoms to gamma rays. So is radiation bad? Is it scary? Well, yes and no. Radiation is another form of energy transfer. It's unique in its method of delivery, but ultimately it moves energy from one end of the room to the other, or one side of the galaxy to the other. Radiation allows us to see the far reaches of the universe, warms our planet from the sun, and gives us tremendous medical technology like X-rays and radiotherapy. But radiation can also give us sunburns, cancer, and the most dangerous weaponry we've invented to this point. So maybe the better question is not what makes radiation good or bad, but rather how can we use radiation? How do we spend our energy? If you like what you heard here and want to learn more, the content of this episode comes in part from the OpenStack textbooks University Physics 2 and 3, as well as other sources which you can find more information about in the description. If you would like to view a transcript or want to cite this episode, that information is also in the description. Intuition is an independent project currently run only by myself, so if you want to hear more, please share this with your friends and family. Your support is invaluable. That means valuable, by the way.